Here in this video we continue looking at various logic gates. We've already looked at the NOT gate, the AND gate, and the OR gate, and we're going to start this video with the NAND gate, which is short for NOT AND. And here's the logic symbol. So it's just like the AND gate logic symbol, but there's this bubble that's on the output. And here's the Boolean algebra for the output, which is A ANDed with B and the whole thing knotted. So a NAND gate is equivalent to an AND gate with an inverter on the output. Now here is a circuit that will give you the truth table of a NAND gate. Now we're not going to analyze this circuit like we did with the AND and the OR, because this is an assigned homework problem. So the approach that you use to analyze this, to show how this circuit gives you this truth table, is the same approach we used in the previous two videos. But you can see how if you compare the output of a NAND to the output of an AND, okay, which is right here, you can see that well, the output is knotted. So again, a NAND gate is the same as taking an AND and putting an inverter on the output. Okay, where here the inputs are A and B, and the output is F. Okay, so the symbol, the logic symbol of a NAND, okay, with the little bubble on the output, that's to signify that there's an inverter on the output, that the NAND is an AND with an inverter on the output. See, that bubble is this bubble here. Now there's also a NOR gate. So here is the NOR gate symbol, and a NOR gate, or NOR, is equivalent to an OR with an inverter on the output. Here's a circuit that will give you the truth table of a NOR gate, and this is another assigned homework problem where you'll prove where this truth table comes from, again with the same approach we used with AND and OR. And if you look at the output of a NOR and compare it to the output of NOR, you can see that the output's just inverted. So again, the NOR is the same as an OR gate with an inverter on the output. Again, output F, inputs A and B, and the symbol of the NOR with the bubble there, again, indicates an inverter on the output of an OR gate. Alright, well, there are other types of logic gates. Let's look at some others here. Okay, this is an exclusive OR. Now, the gates we've covered up to this point, the NOT, AND, OR, NAND, and NOR, those 5 gates are referred to as the basic logic gates. The exclusive OR is a type of what's called compound logic gate, because you can make an exclusive OR out of the basic gates. So you see the exclusive OR, which gives you this truth table here, which is, you know, different than the previous truth tables we looked at, because if you take a look at this truth table, you can see that an exclusive OR, you'll only get a 1 out when the inputs are different. When the inputs are the same, that's when you get a 0 out. Now this is how you build an exclusive OR. It takes 3 basic gates, an AND, an OR, and a NAND. And one thing that I like to do throughout the digital block of this course is count the transistors that it takes to build various devices. And if you recall, the AND gate, which was the first gate that we went over, it takes 3 transistors to build a 2-input AND gate. It also takes 3 transistors for a 2-input OR. It only takes 2 transistors for a 2-input NAND. That was the very first logic circuit of this video. So 3 transistors, 3 transistors, 2 transistors. So it takes a total of 8 transistors to build an exclusive OR. Now, you might suspect, since we have AND and NAND and OR and NOR, that, we could have an exclusive NOR. Okay, so here's an exclusive NOR where if you compare the outputs of this exclusive NOR to the exclusive OR, you'll see that the output is opposite. So here you'll get a 1 when the inputs are the same and a 0 when the inputs are different. And then here's the circuit that you need in order to build an exclusive NOR, and it takes 7 transistors, 2, 2, and 3. Alright, so those are your logic gates. Now, there are 2 families, or popular families, of integrated circuits where the gates are built on. There's what's called TTL, which stands for transistor-transistor logic, and there's also Cmos, which stands for complementary metal oxide semiconductor. And TTL ICs, their logic circuits are made with bipolar transistors, BJTs. Cmos logic circuits are built with FETs. So the examples that we've been seeing in these videos have been examples of Cmos logic circuitry. But like I said, you could build all those gates that we looked at that were built with FETs. You could build them with BJTs. Now, what decides what type of IC you use, whether it's TTL or CMOS? Well, it goes back to the things we talked about with the differences between bipolar junction transistors and field effect transistors. Remember, FETs consume less power because of that high impedance that's on the gate, but BJTs tend to operate faster as switches. So what determines whether you go TTL or CMOS is what's most important in an application. If you need really fast transistors, you need logic circuitry that works at high frequency, well, you would tend to use TTL. If you need low power, if that's really important in your application, well then you would go CMOS over TTL. Okay, because since the CMOS uses FETs, they use those ICs use less power than the TTL. Some other differences here: TTL is more robust against static. Okay, CMOS FETs are very prone to static electricity damage, so you got to take precaution handling them. You know, anti-static equipment and like grounding yourself so the static on your skin doesn't damage the ICs. And then also there's a big difference in power supply requirements for the 2 different types of ICs. TTL, very rigid. You need plus 5 volts, plus or minus a very small tolerance, just a couple of tenths of volts or so. So your 5 volt source has to be highly regulated. CMOS, you can use a range of input voltage. Here's an example of, you know, a couple of volts up to 18 volts. Now, the last thing I wanted to talk about here is just that on Polylearn, there's this PDF that is a summary of all the different gates with the symbols, the Boolean algebra expression, and also the truth tables for 2 input. On any sort of quiz or test, this handout would be provided. I don't expect you to memorize truth tables as non-majors, but I expect you to understand the truth tables. One example of what I mean by understand a truth table is that even though this truth table is for a 2 input AND, you should understand what it would be if it was a 3 input or a 4 input or an 8 input, or, you know, no matter how many inputs, right? Because the concept of the table remains the same no matter how many inputs, right? We talked about that in a previous video. For example, if you had a 4 input AND gate, well, it would take all 4 inputs equaling 1 to get a 1 out. If at least one of those 4 inputs is a 0, then you get a 0 out. And same thing with these other truth tables. Now, an inverter always has just 1 input. You don't have multiple input inverters. But all the other truth tables here, you should understand what they would be for multiple or more than 2 inputs.